All right, guys, Mr. Antonucci here, and in this video, we're going to talk about section 7.3 slope fields. And our objective for today is to use a slope field to represent the solution to a first order differential equation. So in the previous two sections, we found the general solution to two kinds of first order differential equations. The first is where dy dx was equal to f of x. And so to get y, we just took the antiderivative of f of x dx, where the antiderivative could be found. The second kind was separable, and that's where dy dx was m of x over n of y. And you could separate those by collecting your y's and dy's on one side and your x and dx's on the other and integrating both sides. But in a lot of cases, finding the general solution of a first order differential equation is not possible because the differential equation, is a function of x and y. So we use the method of slope fields to obtain information about the solution. And this is one of several different methods, but we're going to focus on this one. So to find the solution to a first order differential equation, we can plot what's called a slope field. So if we draw small line segments representing the tangent lines at various points in the domain of f, and the reason we use tangent lines is because if we know the differential equation, that's essentially telling us the slope at any point. The resulting graph of those little tick marks of tangent lines at different points is called a slope field. And this gives us a picture of the family of curves that make up the solution to the differential equation. And then if when drawing a slope field, we choose only points x comma y where both x and y's are integers, then we call those points lattice points. All right, so let's look at an example here to help solidify our understanding here. So we're going to use a slope field to represent the solutions for dy dx equals y. So first thing we're going to do is draw a slope field that represents the family of curves that are solutions to this differential equation, and then we'll go from there. So if you notice, the differential equation dy dx says that the derivative, the rate of change, is equal to y. Therefore, it doesn't depend on x. And so the derivatives dy dx at all points are of the form x comma y naught. And they're all equal. For example, all points x comma 2 and the slopes of the tangent lines to the graph of the solution of the differential equation equal to, because if no matter what x is, dy dx equals y, which in this set of points would be 2. Okay. All right. So if we go up to where y equals 2, all of the slopes along that would be 2. So we could draw tick marks with slope 2. Okay, if we picked another y value like 0, because dy dx again is equal to the y value, the slope is 0 at all of those points. So if I just pick a different color, then all the points along the line y equals 0 are going to have a slope of 0. All right. The slopes for at y equals 1 are all going to be equal to 1. Okay. At y equal -1, they're all going to equal -1. And so we're starting to get a picture of what the slope field would look like. And this is going to help us get a picture of what the particular solution or general solution or family of curves would be. This one up here at y equals 3 is going to have a slope of 3. So if we keep going on up, we're going to get steeper and steeper and steeper. All right. So we're going to, in part B, use the slope field to draw the graphs of the members of the family of solutions of differential equations that satisfy 4 different situations. So part 1 is when y equals 2, or y equals 2 when x equals 0. So if I look at that point, that's going to be this point right here, 0, comma 2, essentially. So what I do is mark that point on the slope field, and then moving first to the left and then to the right from that point, I just follow the tangent lines as I draw and draw a smooth curve. So if I move to the left, it's going to go like this and then level off here. And to the right, it's going to get steeper and steeper. Okay. If I do the next one, that's going to be the point 0, comma 1 right here. And the solution curve is going to look like this. Okay. Now, if I do the third one, that's 0, negative 1 right here. The graph's going to look like this. So you want to try to start at your point and then move to the left, drawing a smooth curve, and draw your curve to be kind of parallel to the tangent lines around it, following the curvature of those curves. Okie doke. And then one last one, when y equals negative 2, it'd be this one. And then it goes like that. All right. So for this one, um, the differential equation in this example is what we call separable. In other words, if dy dx equals y, then you could have dy over y equals dx. And then you integrate it, and you would have natural log absolute value of y equals x plus c, where c is a constant. And this confirms what we got here, because if we solve this, you exponentiate each side, and you would have absolute value of y equals e to the x plus c. And if you take off the absolute values, that means the other side could have been positive or negative, e to the x plus c. So again, this confirms that the graphs that we have up here in our graph that we did on the slope field are reflections about the x-axis of vertical shifts of the exponential function y equals x, which is essentially what we have right here. Now, I want to show you this in Desmos real quick. Okay, so I have a general slope field here, and then for example 1, we have here's natural log absolute value y equals x plus c, and then I'm going to graph it for two different c values when c is 2, or when c is natural log 2 and natural log 1. This is essentially going to draw the solution curves that we got when we drew the slope field. Okay, and then I could put different points in here and get different solution curves. But you see how this curve right here at 0, 2 goes through the point 0, 2, and to the left it follows the tick marks, and to the right it follows the tangent line tick marks. Okay, all right. So moving along to our next example. Number 2, we want to draw the slope field that represents the solutions to dy dx equals x squared minus 2x plus 3. So since this differential equation doesn't depend on y, dy dx is all points of the form x naught comma y are equal. So for any choice of x, the slope field along that vertical line where x is going to consist of short parallel lines. So if I start with dy dx equals 0, I can factor this and get x minus 3 times x plus 1. And so that's going to give me x equals 3 or x equals negative 1. And the reason I did that is because if the slope is 0, then that's going to make drawing the tangent lines very easy. Well, since this is just a quadratic formula or quadratic expression, can factor it, and then I know that along the vertical line x equals 3, the tangent lines are going to have a slope of 0, and same thing at x equals negative 1. So here along the vertical line x equals negative 1, my tangent lines are all going to be horizontal. And then above on the line x equals 3, tangent lines are all going to be horizontal for that one. Okay. Now, the next thing we can do is investigate the behavior of tangent lines on each side of -1 and 3. So, for example, if x equals -2, dy dx equals 5. So the tangent lines have a slope of 5 for -2. That means they're very steep when x is -2, like this. Okay. If x equals 0, dy dx equals -3. So you're going to have a steeper negative slope here. Okay. If x equals 1, then dy dx equals -4. So they're going to be even steeper, like that. And then if x equals 2, dy dx equals -3. And all I'm doing is plugging x, the value of x, into our differential equation to get the slope. So at 2, the slope is -3, so it's going to be less steep, like this. And then at x equals 4, the derivative would be equal to 5. So again, we're going to have a positive, very steep slope at these points. Okay. So that's the slope field. Now, if you're doing the AP exam, they're typically not going to give you this many points. They might give you like 8 to 12 points. And you can just plug in the X and Y coordinates for each of those points to draw the tick marks for the slope field. But in part B, we're going to draw the graph of the particular solution if x equals 0 and y is 2. So if x equals 0 and y is 2, we're talking about this point right here. And so what we want to do is start moving to the left and follow. So we have a horizontal tangent line, which means we're going to have a relative extrema, possibly, especially since the slopes go, the tick marks change direction there. Okay, then we go like that. And then to the right, it's going to get steeper, but then less steep. And you're going to have a horizontal tangent line at x equals 3, and then it's going to change direction and go like this. Okay, so this is interesting because the differential equation in this example can actually be solved because dy dx equals x squared minus 2x minus 3. So if I have dy dx equals x squared minus 2x minus 3, then y is equal to the antiderivative of that. And I can actually solve this. So that'd be 1/3 x cubed minus x squared minus 3 plus c. And then I could use my initial conditions when x is 0, y is 2. So the function, if x is 0, that means c is going to be 2. So this would be 1/3 x cubed minus x squared. I forgot the x on that. Minus 3x, what was it? 2. Okay. And if you drew the graph of f of x here in Desmos, you could see that it is a cubic function and it would look very, very similar to what we have here. All right, moving on to number 3, we're going to use a slope field to represent the solutions of dy dx equals y minus x. Now, again, we could go through and get the coordinates of each point and plug those x and y values in to this differential equation and draw all the tick marks separately. But it's good to look for patterns here. And so that sometimes helps you get a visual depiction of what's going on. So this differential equation depends on both x and y. We looked at an example where it depended just on y, one where it just depended on x. In this case, it's depending on both x and y. So the easiest thing to do is let x minus or y minus x equal k, where k is a constant. So if k equals 0, then y minus x equals 0, which means that y equals the x value. So um, then we're going to plot horizontal slope lines along the line y equals x. Okay, so if y equals x, then y minus x is going to be 0, so that means the slope is going to be 0. So along the diagonal line y equals x, we're going to have slopes that are all 0 along that line, like this. Okay, and then if k equals 1, then y is going to equal x plus 1. All right, and then so dy dx is going to equal 1. All right. So if I'm along the diagonal line y equals x plus 1, then all the slopes along that line are going to be a slope of 1. So like this. Doop, 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 doop. All right. And then we just keep going like this, so forth and so on. So if k equals 2, then y equals x plus 2. And if I substitute y equals x plus 2, then that's going to mean that dy dx equals 2. Okay. So then I would add short lines with slope 2 to the slope field along the line, the diagonal line y equals x plus 2. Okay, so they're going to be a little bit steeper, like this. And I could continue that pattern with k equals -1, k equals -2, and so forth and so on. And we would see that the slopes over here would be -1 along this line, and then -2, and then so forth and so on. And we would construct the rest of the slope field. All right. Last thing I want to look at is sometimes you might get a multiple choice question where you have to interpret a slope field and match the differential equation with the slope field. So we want to know which of these differential equations could have the slope field shown here. So one of the things that's important to note is that tangent lines that lie along the vertical line all have the same slope. So right here, all of these have the same slope. Okay, that is for a fixed number x, dy dx is all going to be the same. Okay, this means dy dx does not depend on the value of y. If you look at any vertical line, all the slopes are going to be the same along that vertical line. So that means as the value of y goes up or the value of y goes down, it's not going to change the slope. Therefore, the slope field does not depend on y. So the differential equation shouldn't have an equation that involves y. So we can eliminate b and d. Okay. Now, the points in quadrant 1, if you look in quadrant 1 right here, all of those points have positive slopes. And also quadrants or 1 and 4 all have positive slopes. And then quadrants 2 and 3 all have negative slopes. So that means basically when x is positive, the slope's going to be positive, and when x is negative, the slope's going to be negative. That aligns with equation C, not A. That's the reverse of what we did. All right, guys, that's it for this section. Hope that was helpful to you. Make sure you reach out if you have any questions. Take care.